Just what you've been waiting for. Two structural engineers standing between you and dinner. So let's get started. Thank you, Anthony. Charlie and I are going to bounce back and forth here and go through our presentation. And we thought we'd start basically, or go through, not just showing you some projects, but a little story about our learning and teaching experiences, so to speak, from a certain select group of projects, which many people, including people in this room, have contributed to. So we want to take you through this little scenario. But probably first and foremost, this award is named after Fazla Khan, who was one of my heroes and a great engineer from SOM, who not only was a great engineer, but always contributed his ideas and set standards in the industry. And he worked very closely with the Council on Tall Buildings and Urban Habitat. And going back somewhere around 1980, they published this guide towards the different types of building systems that we could use for high-rise buildings. And as we get taller, we have to change the building systems, because if you don't keep using more and more efficient systems for taller buildings, as you can see in this curve, you're going to get into an area with an inefficient system that's going to cause you a lot more weight in your building, as opposed to a more realistic premium for wind when you use the better systems. And also at that time, you can see there was still an emphasis on thinking more about steel for super tall and very tall buildings than concrete. And that started changing. A lot of other systems started coming into play since then. Some of them combinations of the systems that Fazla Khan was showing in his chart, but getting into super columns and super frames and concrete, which kind of brings us to the really the beginning of our history with tall buildings, where we use both concrete and steel together. And Charlie, I think you remember one of the main lessons that we learned on this building was the seriousness of differential creep and shrinkage when you try to mix concrete with steel.
This was the tallest building in Florida. It was the first building designed in one of the strongest hurricane wind locations. We actually went down to Birmingham to the Southern Building Code, and we got the code changed in our favor. But one of the great stories was, you know, in the United States, we have some strange rules and regulations, and iron guys don't like concrete guys working over their head. And so if you look at the Shard recently in London, where they went up together, they wouldn't let us start steel erection until the core was up. And I was standing on the corner one day, and a guy comes up to me, and just the core is up, and he says, "Wow, they're pretty small floors." And what are those doors? What are those windows? Then the building started getting built, but this was the tallest building, and this was the beginning of integrating not only great structural engineering, but great geotechnical engineering. There were no piles under this building. We heard about the 600-foot pile. They drove an H-pile 600 feet. They just kept adding pieces onto it. And we brought in Langen, and we put this on a soil cement mat, a roller compacted mat, and there were no piles, okay? And to me, the collaboration of all the disciplines, including geotechnical, is the key to success in projects.
We were very proud about this building on the East Coast, doing a composite building like this. But, you know, you come to Chicago and they go, bah, bah, bah. We do that kind of stuff all the time, all right? After that, we got a little ambitious in Pittsburgh, where we did the Bank of New York, that's what it's called now, Mellon Bank Center. Our client at the time was actually U.S. Steel, and they wanted something innovative with steel. So building on Fazla Khan's tube concept that he was promoting, we did this stress skin tube, where the actual skin of the building is a steel facade, and the skin of the building helps resist the sway of the building. But the tube structure itself is only used for the code-required strength of the building. By doing that, we were able to not fireproof the facade. Now, that sounds like a very logical thing, but it took like months to convince the local building department that we could do this and still meet the code requirements and not by not fireproofing the steel. Of course, it really helped to have a client that was U.S. Steel at the time to pay for the aspirin for the extra aggravation to get this done. But we think it's significant because moving forward to today, the concept is used in other buildings. As one example is the New York Times Tower, where there's external bracing that contributes only to solving the sway problem with the building, so therefore does not have to be fire protected. So we think it's important to learn from each of these instances and see how they could be used in the future on other projects. And we think it's important for the students here to always look at each project that you see and see what can be learned from that project that can improve the projects of the future. Now, just getting back for a moment to Fazla Khan's chart, okay, one of the things in that chart that's almost become ubiquitous is the use of outriggers. They are used constantly. They're used with all the other systems. Council on Tall Buildings and Urban Habitat has a special task force just to study the most efficient ways of using outriggers. And there's many ways of using them. And one of the projects we were really very proud of that we did with Murphy Yawn was using them in a way of having super diagonals that transferred the load not only to the outside, but with band trusses, put all the weight in the major columns on the outside, these super columns, which is a concept that we're using more and more now on very super tall buildings.
And what this was an outgrowth of looking at sailboat rigging, looking at mast spreaders and stays and guys. And essentially, if you look at a mast, it's basically pin connected at the deck, but it's still a very effective, tall structure. So working directly with Helmuth Jahn and his team, we came up with these multiple outriggers. We tested it in the real estate market because there were going to be certain columns moving out from core to the exterior wall at different locations, I think at about 3 locations. And Bill Rouse and Joe Denny and Liberty Property Trust basically proved that these outrigger columns did not affect rentability at all on any of those floors. So this building came in about 17 pounds of steel per square foot, which at the time was the 9th tallest building in the world, 945 feet.
And outriggers are very useful in a lot of applications. Here in what was at one time the tallest building in Australia, we utilized them in a skewed way. And when I mean skewed, if you look carefully at this diagram, this part of the outrigger here is not in the same plane as that part of the outrigger, as you can see from the interesting geometry. But one of the things we learned in this building is the geometry was perfect for the location and the site on this project, but it wanted to have a torsion problem. It just insisted on having a torsion problem.
Well, one whole face of the facade is curved like a wing, and guess why airplanes fly or lift? So we have torsional TMDs in this building.
Yeah, and
to get rid of those torsional modes.
And the tune mast damper was needed only for torsion, not for the regular lateral loads. So another lesson learned. And then
this was an interesting project because I was walking through Harry Weiss's office, and Harry in about 1981 was getting into twisting buildings. Now everybody twists buildings, but Harry was kind of going about it, you know, this is pre-BIM, this is pre-Geary, this is pre-CATIA, this is pre-everything. And so I went back to Harry and I said, Harry, why don't you just take the top and twist it 45 degrees? And this project came out in 1983. Engineering News Record had a cover story called How Tall? This was 2,500, it's actually 2,500 feet, I think. That says 2,000 feet. But it put us on the map as people that could do a 2,000-foot building. And that's kind of an interesting way to sort of promote yourself. If you do it, people start to think that you actually can do it, and guess what? We can.
But one of the other interesting things that came out of this, significant design was done, and then there were wind tunnel tests done with RWDI, and there was actually in the wind tunnel test, there was a little gizmo at the top where you could move something and you could adjust the amount of damping that was in the building. So looking at that damping, you could see the significant change in accelerations and deflections when you had the tuned mass damper, okay, as opposed to without the damper. But the interesting thing is this was studied more generically and just looking at it from the point of view of damping values. As you can see on these charts, and these are the original charts, you can see they haven't been redone. Just going from a damping value of 1% to 2% was a significant difference in the accelerations at the top of the building, which encouraged us more to look at concrete for super tall buildings, because that's the difference between, typically, approximately, between the intrinsic damping that you get in a concrete structure, about 2%, and what you get in a steel structure, about 1%. So starting to look more and more at concrete for super tall buildings started us to get together with Miglen Beitler and looking again in Chicago, looking at a tall building design.
This was Caesar Pelli. He had just finished 181 Madison with Paul Beitler and Lee Miglen, and they bought the site right across the street. And there's some really interesting things about this. We came out here and we started testing high-strength caissons, 18,000 PSI, 20,000 PSI concrete. We researched dolomitic limestone and concluded that Chicago probably had the best concrete in the United States. That building was only 120 feet by 120 feet, and it was about 2,000 feet tall. I mean, this thing was skinny. But if you look at those outrigger columns, we were able to cross the property line and put a doorway through them at the street level. And the end result was we came up with a building very, very skinny, very, very tall. We played with the mass, we played with the density, we played with the damping coefficient, and this building would not have had a TMD in it.
That led to Petronas Towers.
Paul Beitler always likes to, when I talk to him, give me a little jibe. He says, you know, I paid you guys all this money on that project, and we never built it. It was 91, the market went into the tank. So Caesar Pelli's gang and we went to Malaysia. We entered a competition. We basically took everything we learned in Chicago and we applied it to a concrete tall building with a central core 70 by 70 and a soft tube with 16 columns around about 150-foot diameter. And we introduced high-strength concrete and structural steel into the Malaysian market. Why? Number one, we thought it was right. Number two, we had technology transfer built into our contract with Petronas and the Prime Minister.
You can see here the steel floors working with the concrete, just an example of the combination.
When we arrived in Malaysia, it took 14 days to do an office building in concrete with beams and slabs. We did this, but once we got up to speed with Laird McGovern Bovis, we were doing a floor every 2 days.
And this building was done without any additional damping. But we still like steel. And in the next tallest building in the world, Taipei 101, was actually basically a steel structure. And here you can see being introduced certain elements on the facade to break up coherent vortex shedding. And this building was primarily all steel, but it had probably everything that was on Fazla Khan's chart was somewhere in this building, including a core, including the outriggers again. This is actually a tube on the outside that works together with that. Seems like a lot, but if you looked at the design requirements for this building relative to wind, typhoon winds, and seismic.
And seismic, yeah. We didn't have seismic in Malaysia.
Yeah.
So we could make the mass higher and not really have the penalties of seismic even though when the tsunami hit, the Petronas Towers did move a little bit.
But also there is concrete in this. Those super columns are steel encased concrete, and you can drive probably a small pickup truck through them if you lay them on their side. And again, the value of these tall buildings, the esteem value, I think is shown in this photo and how it contributes to the environment. But something else was done on this building that was interesting. Maximum use was made of the tune mass damper. It was shared with the public, and it became something that the public could go up to the top of the building, can still go up to the top of the building, and observe the tune mass damper in operation. If you want to do it, pick a windy day, you'll have more fun. Now, all of these buildings have a lot of things in common, but one of the things that stands out is the challenge to the structural engineer, especially with the dynamic analysis of buildings, is when the buildings are very, very, very slender. And Plaza 66 in Shanghai, okay, it's 2 towers that are very, very slender. And at the time, I believe they were the tallest concrete buildings in China. And they're all concrete, and they're based on the supply of local materials. They were not extremely high strength concrete, probably something in the order of 60 MPa, I remember. But here we are doing this thing. We think we have a good solution, and then we're hit with the local code in that area, and the Chinese code that was being used, and they said the sway on the top of the building could not be any more than the height of the building divided by 8,000. Okay. Now, as some of you know, the typical range is for that. Very seldom it's a code value, but it's more in the range of the height of the building divided by 500. And on very tall buildings, we go to 400, 450 or so. So Dennis Poon from our office, who many of you know, he's a director at the council, fluent in Cantonese, had to get fluent in Mandarin to convince the authorities there to allow us to really design this building based on what the wind tunnel tests were doing, and we finally were able to get it with an L over 500 approximately sway. And that was kind of the beginning for us. And at the same time, I believe, or right after that, I think SOM was going through similar things with their tower in Shanghai. And that kind of work with engineers visiting these areas contributed a lot to the codes that they have there now, which make a lot more sense. But getting back to Chicago, we always come back to Chicago and talking about slender buildings. The beloved Santiago Calatrava Chicago Spire that so many Chicagoites were looking forward to seeing was an extremely challenging project and something we learned a lot from. This project was so slender that more than one mode of vibration was active in the dynamics of the project. And actually, as you can see in this study that we did with RWDI, you would actually get the vortex shedding problems at the lower wind speeds, like 1 month return or 1 year return, as opposed to the wind speeds that we normally use, something in the order of 10-year wind return. So it was a learning experience on how to really deal with these extremely tall, high period, slender, tall buildings. And many of the structural engineers out there who are doing super tall buildings are familiar with this. And the same kind of thing occurred on Shanghai Tower. And on Shanghai Tower, using the twist of the building, okay, which was also major use on the Chicago Tower, we minimized the effect of coherent vortex shedding, basically changing the frequency of the vortex shedding as you go up the tower, so it doesn't cause resonance with the frequency of the building. The wind forces in the crosswind direction was significantly reduced. I think there was a 60% reduction, 60% reduction in the overturning moment due to crosswind vibrations. And I think this is an excellent example of what Charlie was pointing out before, of how the more we go in the direction of integration between engineering and architecture, construction, and all of the other disciplines, okay, the better our projects are and the more efficient they are. So it all gets down to integration of engineering and architecture, whether it was Gaudi's structure that was trying to integrate these domes in such a way that they didn't require, making them so thin and slender that they didn't require any buttresses, the jagged edges of the Petronas Towers that helped break up vortexes, and the total integration of the sloping walls of Kingdom Tower, which Thornton Tomasetti is now doing with Adrian Smith and Gordon Gill Architects. The sloping walls, structural walls that are sloping, are actually the walls that develop all of the architectural spaces. We're always talking about integration of engineering and architecture, and I think that's where the future really really lies. I just want to end, I think Charlie and I want to end just mentioning 2 or 3 things we feel very good about today. Okay, one is the fact that we were proud that the Thornton Tomasetti contributed to one of the award winning projects today that you just heard about. The other is very proud about the numerous high-rise buildings that the firm has done, both during the time that Charlie and I were extremely active there, and the ones that are still being done. But most of all, okay, the people. All of the people in the firm and the people in other firms that we've collaborated with and our clients. It's that collaboration that Charlie was talking about before that's assisted us in our career, in our work, and it's that collaboration, I think, that will make everybody's firms be successful in the future. You want to add anything to that, Charlie?
I just want to thank the council for honoring Richard and me. A lot of people don't know this, but we went to college together. We went to graduate school together. That goes back a long time. I hired him in 1968 because he was one of the smartest guys I knew. And we took Thornton Tomasetti from about a 10-person firm to a 600-person firm. So it's been a real roll. It's been a real ride. So thank you very much.
And thank you, Anthony. We still like each other.